제가 지금 그 양력 자료를 못 받아가지고요. 지금 양력을 설명드리는데 일본에서 영국 다이스 스타트 받으셨고 굉장히 액션을 하신 리서치 프로페서도 알고 그래서 좀 양해하시고 지금 오늘 원래 이게 과장이 차우성 교수님이죠. 발표가 그렇게 갑자기 바뀌어서 제가 양해 주십니다. Please welcome Professor.
Good afternoon, ladies and gentlemen. I'm very glad to join this annual spring meeting of Polymer Society of Korea, and I'd like to thank the committee for giving me this opportunity. The title of my talk is the Online Coupling of Liquid Chromatography NMR for Polymer Characterization. Online LC-NMR is a kind of hydrated technique which uses an NMR spectrometer as a detector of liquid chromatography. As you all know, both NMR and liquid chromatography gives a lot of information about polymer structure. So the combination of liquid chromatography and NMR would be promising for advanced characterization of polymers. Online coupling of liquid chromatography to NMR was first recorded in 1978 using 60 MHz NMR spectrometer. At that time, the combination of liquid chromatography with NMR seemed rather impractical because of the low sensitivity of NMR as a detector of liquid chromatography. But recently, the introduction of ultra-high field magnet up to 800 MHz greatly increased the sensitivity of NMR. More important is the instrumental developments of the interface of liquid chromatography and NMR. So nowadays, the dedicated NMR probe is commercially available, so you can easily do this experiment. Another important development is the development of the method of suppression of large signals due to solvent. This technique allowed us to use a variety of mobile phases for liquid chromatography. This extended the usefulness of LC-NMR. This is a picture of our LC-NMR system using a 750 MHz NMR spectrometer. This is a liquid chromatograph and column is here, and the outlet of the liquid chromatography column is directly connected to the dedicated probe, which is inserted in the superconducting magnet. From the viewpoint of polymer characterization, online coupling of size exclusion chromatography with NMR, because it's SEG-NMR, is the most straightforward approach, because SEG is the most widely used liquid chromatography in polymer science. Over the past 10 years, we studied about the characterization by SEG-NMR, and it was proven that this has been proven to be useful for the analysis of polymer structures such as homomer composition, statistics, or irregular structures as a function of molecular. Today, I'd like to show you two examples of polymer characterization by LCNMR. The first example is the analysis of chemical composition of ethylene copolymers, including a small amount of dyeing units, in this case, ethylene organic, by SUCNMR. Because the property this polymer is important hydrocarbon elastomers known as EPDM. Since the property of this material depends on both molecular weight distribution and chemical composition, so the analysis of the molecular weight dependence of chemical composition is very important for understanding of the structure property relationship of this polymer. For example, crystallinity and oxidative stability, or vulcanized and mechanical rheological properties of EPDM is very dependent on chemical composition and molecular weight distribution. So the analysis is very important for the industry. And also, the information on chemical composition against molecular weight is also useful for understanding of mechanism aspects of polymerization mechanism, in this case, zero-granata polymerization. You see here proton NMR spectrum of EPDM. This is the resonance between propylene methyl group in the protein, and this is the signal due to methylene units in ethylene. Methylene protons in ethylene. And these small resonances are due to these not ethylene non-bonded units. And these small splittings are due to the integrated and filament isometric structure of this diamond. The online distribution measurement of this EPDM was carried out using nucleated protocol methodology. And the amount of sample used for the analysis is 0.5 milligram or less. The flow rate of the liquid is 0.2 milliliter per minute. And 8 scans were accumulated for each specimen. And the total of measurement was about 60 minutes. This is the resonance due to the methyl group in the protein. This is the resonance due to the methyl group in the ethylene. So cross sections of these resonances with H1 detected SVC curves, which will be shown in the next slide. These are the H1 NMR detected SVC curves for detected for ethylene units and protein, and 3 different samples. The sample A has a larger average molecular weight and higher protein content compared with sample B. And this sample is a test sample, which was prepared by mixing sample A and B in equal amount. And you see here, the ethylene content determine the ethylene content as a function of molecular weight for sample A, B, and the test sample C. And the solid line in the solid curve is the expected curve on the result of sample B. As you see here, the plot for sample C agrees well with the expected curve. So this demonstrates the reliability of SEC NMR for quantitative analysis. Under the conditions mentioned above. This is a spectra measured under normal conditions. As you see here, the signals due to messengers and messengers both have high signal to noise ratio, almost comparable with that obtained by normal procedure. However, small resonances due to a small amount of dioxide are too weak to be detected under continuous flow mode. So, in order to determine a small amount of dioxide, we perform SEC NMR under the stop and flow mode. In the stop and flow mode, the flow of the chromatography was broken at these 4 points, and scans were accumulated to increase the extent of the spectrum. By this technique, we can observe rising. This illustrates SPC NMR analysis of ETBN sample. Using continuous flow SPC, you can determine the ethylene content as a function of molecules. And using the stop and flow SPC, you can also determine the small amount of dioxide as a function of molecules. As you see here, the ethylene content decreases with decreasing molecular weight, and also the dioxide has the same tendency. This can be related to the mechanism of characterization. The second example I'm going to show you is the distribution analysis of fluid ethylene saturate by LCCAP. LCCAP stands for liquid chromatography as a critical absorption point, which is a chromatography of the polymer performed under particular conditions. You see here a diagram of elution behavior of polymers in 3 different modes of chromatography. In side exclusion mode, polymer molecules with larger hydrodynamic volume, Lewis class. In the absorption mode, polymers with high degree of the elution order is reversed as in SEC. Molecule with higher degree of polymerization is absorbed in a larger extent. At the critical absorption point, where size exclusion effect and absorption effect are balanced, all polymer molecules are eluded at the same retention volume, regardless of molecular weight. Accordingly, we can get small changes of polymer structure such as toxicity by the chromatography carried out at the critical absorption point. In order to demonstrate the toxicity separation by LC gap and real-time detection by toxicity separation by NMR, we have chosen polyester saccharide as an illustrative example. This is because of several reasons. One reason is that we can prepare a wide variety of polyester saccharide by controlled polymerization. The second reason is that this polymer is soluble in many organic solvents, regardless of toxicity. Another reason is that this polymer allows us to determine its toxicity by proton NMR. This is essential for this step. Ethyl methacrylate can be polymerized in a living and stereospecific manner. When its monomer was polymerized with tertiary lithium magnesium bromide in the aluminum system, polymer with high isotoxicity was prepared. Whereas the polymerization of this monomer with tertiary lithium in presence of this bulky fluid acid, a polymer with high symbiotoxicity is prepared. When this monomer is polymerized with p-butyl lithium normal butyl aluminum system, polymers with moderate symbiotoxicity are prepared. All the polymers have the same chemical structure except for toxicity. This is the list of the polyester methacrylate samples used for the LC-cap NMR experiment. All the polymers have now molecular weight distribution shown here. And these four samples have high symbiotoxicity and different average molecular weight ranging from 6,000 to 45,000. Using this series of samples, we determine the critical absorption point for highly symbiotic DNAs. In this experiment, we use a curve sample signature bonded to aminotropic groups. So the surface of the stationary phase is covered with amino. When this polymer, the highly symbiotic DNA erupted in the side exclusion mode, as shown. When cyclohexane was added to the element, the elution mode, the elution behavior was changed to absorption. And you can see composition of 3961. We found critical absorption conditions for highly symbiotic DNAs. This is because acetone is a good solvent for DNA, whereas cyclohexane is a poor solvent. Under these conditions, polymers with lower symbiotoxicity still errs in non-critical conditions, so the discrimination of toxicity is achieved. You see here an example of continuous flow LC-cap NMR spectra obtained by this experiment. 8 scans were accumulated for each spectra, and a total of 120 spectra were collected from the emission time to 60. an result of the LC-CAP analysis of model PEMA sample, which has prepared by mixing 4 different PEMA with different characteristics. As you can see here, the LC-CAP proton NMR detected LC-CAP trace shows 4 peaks. And when you look at the plots for RR, MR, and M trial contents against emission line, you will see an almost linear increase of RR trials with increasing emission line. When the same mixture was analyzed by cyclic superclusion chromatography with proton NMR, we observed unimodal distribution erosion curve. Since these polymers have the same molecular weight, the emission curve is values as expected. So the difference of the SCC and the LC-CAP is very clear. Next, we analyze the simple PEMA sample by LC-CAP. The sample was prepared by living anaerobic polymerization using this catalyst. This polymer has narrow molecular weight distribution. An average RR content is about 53%. This is a result of the LC-CAP analysis. And as you can see here, this polymer has a characteristic distribution in which the RR trial content increases from 40% to 80%, about 70%. So this result is rather surprising for us because, as I mentioned, this polymerization is living polymerization. So we have postulated a single site method. However, the analysis of LC-CAP NMR suggests that the polymerization system is consisting of a variety of active sites with different stereospecificity. Usually, polymerization system with multiple active species is a broad molecular weight distribution. But the result indicates that this polymer has a narrow molecular weight distribution. So the result is very surprising for us, and the reason is not clear at present. In this presentation, we talked about we showed two examples of LC-NMR analysis of polymers. One example is show that SCC-NMR is an efficient method for examination of chemical composition of copolymers as a function of molecular. The second example shows LC-CAP NMR, which is carried out under particular conditions. That's enable determination of the characteristic distribution of a polymer sample. Characteristic distribution is a new aspect of the characterization of polymers. So we have devised an experimental method to determine characteristic distribution by LC-CAP NMR. And this information from this NMR analysis is useful for better understanding of structural configurations of polymers, as well as for an understanding of polymerization methods. We hope that this method